and welcome back to our video series on probability. In our last video, we looked at different counting methods. We looked at conditional probability. We looked at law of total probability, and we looked at multiplicative law of probability. Today, we're going to discuss random variable. So what is a random variable? Well, a random variable maps a function from the sample space to the real line. So if we consider this small circle as our sample space, we're basically assigning a real value to this sample. A random variable x associates a numerical value with each outcome of an experiment. Essentially, it's just a scale that we're using to measure our outcome. And so I take some sample from here, and what scale does it have? Now, there are two types of random variables: discrete random variables and continuous random variables. And for the time being, we're going to stick with discrete random variables and look at some of their properties. So a discrete random variable. Here with discrete, we assume only a finite or countably infinite number of distinct values. A couple of examples that come to mind. Suppose I toss two dice. I'm interested in knowing that the sum is 7, not the particular outcome that yielded 7. Perhaps I flip a coin 10 times. What is the total number of heads? I could care less about the heads or tails sequence. I'd just like to know how many heads I got in that flip of 10 coins. Now, continuous random variables, which we will talk about later in future videos, these are uncountable. Examples of these include the time a train arrives at a station, or the lifetime of a battery, or the particular gas mileage for a particular vehicle. Now, there are two types of probability. The first is frequentist, and the second is subjective. And I'd like to look at subjective first. Subjective probability is a measure of one's belief. So if I were to ask you what's the probability it will rain tomorrow, this may vary from individual to individual. It's based on what you believe and your personal experiences. However, with frequentist probability, this relies on the relative frequency of an event occurring. So suppose I flip a coin 100 times, and I'm interested in the number of heads. So what are the number of heads out of the total coin flips? Number of heads out of 100. This is the type of probability we're going to be concerned with. Now, again, discrete, it's countable. So we're interested in whether x takes on some value of x. So what are we talking about here? We're going to say the probability of our random variable x equaling some value. And we're going to define this as the sum of the probabilities of all sample points in S that are assigned the value of x. Well, in shorthand, we can say the probability our random variable equals some value is the probability of that value. So as an example, suppose I were to go fishing. What's the probability I catch 12 fish? Well, my random variable x is the number of fish, and the number I'm looking at is 12. So the probability of my random variable, my number of fish, equals 12 is going to be said the probability that my random variable equals 12, and this could also be written as the probability of 12. This leads into what's called a probability distribution. Now, the probability distribution of a discrete random variable x is a list of the distinct numerical values of x along with their associated probabilities. So the probability distribution of this random variable, we list the distinct numerical values of our random variable, and then we look at their associated probabilities. So as an example, let's let our random variable x represent the number of heads obtained in 3 tosses of a fair coin. How many ways can I get outcomes of tossing a fair coin 3 times? Well, I could get all heads. Heads on the first, heads on the second, heads on the third. I could get head, head, tail, head, tail, head, head, tail, 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 head, head, tail, tail, head, tail, head, tail, and tail, tail, tail. And so the question is, could we make a probability distribution of this? And the answer is yes. And so notice, here's my outcome. I've got 3 tails. I've got 2 tails and a head. I've got 2 heads and a tail. And then I've got all heads. Well, if I have all tails, remember we're looking at the outcomes of heads. If I've got all tails, then I have 0 heads. Here I only have 1 head. Here I have 2 heads. Here I have 3 heads. Now, there are 1, 2, 3, 4, 5, 6, 7, 8 outcomes when we toss a fair coin 3 times. There's only one way that I can get no heads, and that's all tails, and so 1 out of 8. Likewise, there's only one way that I can get all heads, and that is 1 out of 8. However, when I look at 2 tails and a head, there are actually 3 ways that I can get this. So that is 3 out of 8. And when I look at 2 heads and a tail, there are 3 ways I get this. And that is 3 out of 8. And so my discrete probability distribution is right here. Now, for any discrete probability distribution, the following must be true. The probability of my random variable equaling some value has to be between 0 and 1 for all of the values. And if I sum across all of my probabilities, I get 1 because that's all I have. That's everything. So with our probability, we're trying to get an idea of what our data looks like before we ever see the data. What would we expect this data to look like? Now, this is going to be key because it's going to lead into expectations, our expected values. If x is a discrete random variable with a probability function, p of x, we will define the expected value of x to be the sum of x times the probability of x. And that's going to be mu. This is going to be the true mean. Why? Because these are all the values and all the probabilities. So we know this. So as an example, suppose we've got the following probability distribution. X is again 0, 1, 2, and 3, but the probability of x is 1/8, 1/4, 3/8, and 1/4. So if I'm looking to try to find mu, that's the expected value of x, I'm going to sum from x equals 0 to 3, x times the probability of x. In other words, I'm going to take x times its associated probability, and I'm going to sum up all these products. So 0 times an eighth plus 1 times a fourth plus 2 times 3/8 plus 3 times a fourth gives us 1.75. What about variance of x? Remember, these are random variables. And since they vary, there's going to be a little bit of variability amongst all of the values. So variance is going to be defined as the sum of x minus mu quantity squared times the probability of x. And that's going to be sigma squared, our true variance. Now recall our mean was 1.75. So variance of x, this is sigma squared. I'm going to take each value of x minus the mean, so 0 minus 1.75 squared times its probability, 1/8. Here I've got 1 minus the mean, square it, times 1/4. 2 times the mean squared, times 3/8. 4 times the mean squared, times 1/4. And what that gives me is a variance of 0.9375. But we'd rather work with the standard deviation here. We've got a mean that's in one set of units. If we try to use our variance, we're in squared units now. And so it does us no good to talk about the spread about the mean if we're dealing with squared units. So we'd like the spread to be in the same unit. So we're going to say sigma, our standard deviation, is just the square root of the variance. Now our variance was 0.9375. When we take the square root of this, we get our standard deviation is 0.9682458. We can also find expected values of a function. So we'll let g of x be any function. The expected value of that function is the sum of the function times the probability x equals x. So if we were to let g of x equal our random variable x, then we've got the sum of g of x times the probability of x. Well, that's mu. So it's our expected value. And if we let g of x equal x minus mu squared, then we get the sum of g of x times the probability of x. Well, as we can see, this is simply the variance. But instead, suppose we let our function be 3x plus e to the negative x. And so we are going to take the sum of 3 times x plus 2 times e to the negative x times the probability. Well, remember our x values were 0, 1, 2, 3. And so we've got 3 times 0 plus 2e to the negative 0 times, well, this is an 8, plus 3 times 1 plus 2e to the negative 1. This is a fourth, plus 3 times 2 plus 2e to the negative 2. This is 3/8. And 3 times 3 plus 2e to the negative third times its 0.25. And we get 5.810335. Notice what we did. Everywhere an x appeared, we plugged in the value for x and then multiplied by its particular probability. Now, both our mean and our variance are expectations. These are values that we expect. What do we expect our mean to be given our data? What do we expect the variance to be given this particular data? And there are rules for expectation. So first, let's look at the property of means. We'll suppose that a, b, and c are constant. Well, the expected value of a constant is a constant, right? If I've got the number 5, no matter how many 5s I lay out there, it's never going to change. It's a constant. And so the expected value of a constant is a constant. Our second rule, the expected value of a constant times a random variable. Well, we know that the expected value of a constant is a constant, so we can pull the constant out. And we get expected value of a constant times a random variable is the constant times the expected value of the random variable. And our third rule, expected value of ax plus by plus c. Well, here I've got the expected value of a constant times x plus a constant times y plus a constant. Remember, according to rule 2, The expected value of a constant times a random variable is the constant times the expected value of the random variable. So we get a times the expected value of x. Well, here y is a random variable, and so we get plus b times the expected value of y. And then when we go back to rule 1, expected value of a constant is a constant. Well, let us suppose that we've got x1 to xn. We've got n random variables, and they come from the same population. Now, I want the expected value of x bar, our sample mean. The expected value of x bar is the expected value of 1 over n times the sum of the xi's. But 1 over n is a constant. Let's pull it out, and we get 1 over n times the expected value to the sum of the xi's. The expected value to the sum of the xi's is the same as the sum of the expected value of xi's, and so we get 1 over n times the sum of the expected value of xi. Well, what's the expected value of each xi? It's mu. And so we get 1 over n times the sum of the mu's. How many mu's are there? There are n. So we get 1 over n times n mu, and that gives us mu. Now, what does this tell us? This tells us that the sample mean is on average correct for the population mean. Properties of variances are slightly different, however. If we now suppose a, b, and c are constants, if I look at the variance of a constant never changes, so there's no variability. So the variance of a constant is 0. However, in rule 2, the variance of a constant times x, well, I have to pull that constant out and square it. And so I get c squared times the variance of x, and this is because of that x minus mu quantity squared idea. Now, in rule 3, the variance of ax plus by. This is going to be a squared times the variance of x by rule 2 plus b squared times the variance of y by rule 2. But then we've got a covariance term between x and y, and so we have to subtract off 2 times a times b times the covariance of xy. This is provided that our values are dependent. So if x and y are dependent upon one another, we have to take 2 times ab times the covariance of xy. However, there are certain conditions where this goes to 0. And in our next video, we'll look at these conditions. And this is what we hope to be able to obtain. We'd like to see that we don't have dependent variables, and so this covariance term will go to 0. Now, I would like to do a couple of examples in R. I'm going to create this table to show a relatively easy way to create a probability distribution. And so when I run this, here I have my variable x and the probability of x. Here I have my heads. I've got none, 1, 2, 3. This was for our first example when we looked at our probability distribution. There's an easier way to create this, although it is not going to come out like this. So I'm going to concatenate 0, 1, 2, 3 and call that x. And then I'm going to concatenate the probabilities and call that p of x. Now I'd like to calculate the expected value of x. Well, remember, mu is the expected value of x. That is the sum of x times p of x. And so I take each x multiplied by its probability. I add those up, and I should get 1.75. Well, I've called mu the sum of x times p of x. And so mu is 1.75. So far, so good. Let's talk about calculating the variance in a discrete probability distribution. Remember, that's the sum of x minus mu quantity squared times the probability of x. So in this case, x minus mu. X was 0, mu times its probability. X was 1 minus mu times its probability. X was 2 minus mu times its probability. So notice, 0 minus mu squared times 1/8. Plus 1 minus mu squared times 1/4. Plus 2 minus mu squared times 3/8. Plus 3 minus mu squared times 1/4. And what this should give me is 0.9375. So let's take a look and see. I've called this sig2 for sigma squared. And sig2, 0.9375. Notice, the sum of x minus mu squared times the probability of x. What about calculating standard deviation? Well, remember, that's the square root of our variance. Well, we know sigma squared is 0.9375. So if we simply take the square root of that, we get 0.9682458. And I've called sig, that represents sigma. Now, let's finally take a look at the example of calculating the expected value of a function. Remember, it's the sum of the function times the probability of x. We're going to let g of x equal 3 times x plus 2 times e to the negative x. And so I get 3 times 0 plus 2 times e to the negative 0 times 1/8. Plus 3 times 1 plus 2 times e to the negative 1 times 1/4. Plus 3 times 2 plus 2 times e to the negative 2 times 3/8. Plus 3 times 3 plus 2 times e to the negative 3rd times 1/4. And what we should get here, 5.810335. Notice what I've done here. I've got 3 times x plus 2e to the negative x times the probability of x, and I'm summing all of this up, and I get the same answer. Now, you may be asking why I said 2e to the negative 0. There is no negative 0. It's just 0. But I left this negative in, so you would remember that when you plug in your values of x, if it's got a negative, it needs to be there. Don't forget that you've got this negative here. Okay, that's it. In our next video, we will continue looking at probability. See you then.